So the way this is going to be my Microsoft OneNote that you'll see shared, and some of you may need to adjust the screen size when I share it. I'm going to share it now for you so you'll be able to see what I mean. Depending on the type of device that you're using, you might need to use your scroll bars, and depending on the size of your monitor, you may want to make sure that you pull up the recording and you can kind of zoom in and out on things, I'm pretty sure. But I'll try to write large enough where everybody can see it. And see a couple of people there that are that are already doing good with the complex number, so that's certainly good to hear. Those of you that are watching on the recording, obviously you'll be able to pause if you need to take notes, and those of you that are here live, if you need to pause and take notes, that's certainly fine. Wanted to mention, Mrs. Carmichael brought to our attention here some problems with the Unit 2 practice test, so we are going to be dropping that. We will be doing a very thorough review. So, right, and someone asked about what we're covering is complex numbers, operations on complex numbers. That'll include conjugates, review of polynomials and polynomial operations. So this is quite a busy week. There are no pre-tests or dropped assignments or practice tests or anything like that in the content this week. So I will be covering quite a bit. I'm going to have to move fairly quickly to get through everything. So remember, it's very, very important that you're thoroughly looking through the lessons on these. I'm compacting everything into a 1-hour lesson, so it's very important that you go through those. It's very important that you attempt all the practice problems. A big part of that learning process is going to be finding the errors you make on the practice problems. So we talked about radicals last week. So let's say we have something like the square root of 4. We know that that equals 2. Okay, so what we're talking about with complex numbers actually begins with something called imaginary numbers. These are going to be critical as you're going to have imaginary number solutions when we get to our quadratics on occasion and when we get to our higher level polynomial functions. So this is something you're going to see frequently in the course, not just here in this unit. All right, so I suppose if I were to think of the definition of an imaginary number, it would be the square root of -1. As we know, we can't take the square root of a negative value. There's no number that, if we multiply it by itself, would result in a negative number. So we end up, in this case, with an imaginary number. And the imaginary number is part of a complex number. So when you see that complex numbers, it's not just the I here that you see. It's actually, I is just imaginary value, and then that imaginary value is part of what makes up a complex number. So let's go ahead and I'm going to first look at and give you something that ties it back with the radicals that we were working on. Let's say we had something like the square root of 8, for example. You know, we can take the square root of 8. I could write 8 in an equivalent form. Equivalent form, something, actually it was on one, I think, your quiz for Unit 2. We talked about writing equivalent forms of x squared, I believe. That was also the part of the collaboration that we did last week. So it's something very important to recognize as equivalent forms. In other words, I can write 8 in a lot of ways. I could write it as 1 times 8. I could write it as 2 times 4. So there are a lot of different ways. 4 plus 4, I suppose I could write it as. Now, in this particular case, I want to think of a value that's a factor of 8 that's also a perfect square, which is 4. So I'd break that down as square root of 4 times square root of 2. So everything I've written here is all an equivalent form of the square root of 8. Well, the reason I'm writing it in this equivalent form in particular is because I need to write it in a format that's going to allow me to reduce it. As you can see here, we have the square root of a value that is a perfect square, which reduces to 2, and then that would just be 2 times the square root of 2. And of course our multiplication operation is implied, so we would write it something like this. Right? Now your first example in your complex number lesson is square root of -8, so I didn't want to use examples that you already had, so let's use something a bit different. And I'll show you how we get this I value in some of our answers. Okay, so let's say we have the square root of -32. That's a great question, Samantha, and I didn't want to address questions, but yes, I'm a math teacher and my 2's look like Z's. Isn't that terrible? But so when I do write Z's, they'll have a line through them like that. So those are 2's. So I did want to address that as I was going. I didn't want to confuse anyone with thinking that the 2 was a Z, right? So moving on, I'm going to do the same thing here. I've got a -32. Whenever you have a negative value under your radical, okay, we're going to go ahead and make that immediately -1 times 32. Right? The reason I do that is I'm basically factoring out a -1 because the square root of -1 is going to give me that imaginary value I. And the 32 can break down quite a bit as well, so technically we could call this square root of -1 times, and let's do, what is that, 16 times 2, right? Okay, so my 16 is my perfect square that I'm going to be able to pull out here. So that gives us square root of -1 times square root of 16 times square root of 2. We know the square root of -1 we already defined up here as being I, an imaginary value. So I can simplify that. I can simplify square root of 16, that's 4. And then I can also put my square root of 2 here because there's not really much I can do with the square root of 2. We're not going to write this as I4. Those of you that are here in Central Florida, I know we've got a lot of students in Orlando and Orange County and Kissimmee and whatnot. So I4 is obviously a pretty popular interstate highway that runs right through Central Florida, but we're always going to write it with the numerical value before the I. So we'd have 4I square root of 2. And that is how we would simplify that. All right. And as I said, those of you, I do have to cover really 4 different lessons today. So if it is necessary to go back to the recording, I certainly understand that. Those of you that are maybe wanting to write this down, unless you can write really fast, you might need to go back to the recording and pause that. Okay? So, talking a little more just about the imaginary values, we're not moving on to the complex numbers just yet because we need to have a thorough understanding of these imaginary values. So, if, let me show it to you this way. If I had square root of 2 times the square root of 2 would equal 2. So, in other words, anything, if it's a radical, and it's the same radical times itself, it's always going to equal whatever's under the radical. So it works with any number. Square root of 7 times square root of 7 is just going to equal 7. Okay? So if you think about it, the reason why is square root of 2 times 2, we multiply what's under the radical. 2 times 2 is 4, and square root of 4 is 2. All right, so it just kind of saves you a step to recognize that any time there's a radical times itself, it's always going to equal the value under your radical symbol. The same thing works with our, square root of -1 times square root of -1, for example. Even though this is an imaginary value, it still equals -1. Okay, so what that leads us to is the pattern of exponents on I. And there's a chart, I think it's probably on page 2, I'm not sure, I think it's page 2 in your lesson. But you definitely want to make sure you look at that pattern of exponents on I. So If I had I to the power of 1, anything to the power of 1 is always itself. So that would just equal I. Okay, and remember that still I is still equal to the square root of -1, so I mean both of these are equivalent. Now if I had I to the power of 2, we could think of it like this. That's the square root of -1 times the square root -1, which I just wrote up here, just equals -1. The most important ones that you're going to have are I to the first, I to the second, I to the third, I to the fourth, because we're going to show you a way to get to that that value if we're using higher exponents. We're going to show you a little shortcut there. All right, so let's look at I cubed. If you need to work these out, if you don't have them written in your notes, I would suggest you just write I to the first through I to the fourth in your notes and have what those values equal. But this would be square root of -1 times the square root of -1 times the square root of -1. And we could simplify that by just working left to right. So when I do the first one, I'm going to get -1 times square root of -1. Well, I can't really simplify anything else here, so I'm going to write the square root of -1 as I. And you would just have -I. Okay, so that's for I to the third. All right. Now, for I to the fourth, we're just going to add that extra square root of -1 over here. And you're actually going to end up with a +1 when you do I to the fourth. And just based on time, guys, I'm not going to actually multiply it all out and simplify it. But if you do square root of -1 times square root of -1 and you do 4 of them, you're actually going to end up with a +1. Okay? Why is it important? Why are we only going to I to the fourth? Well, I'll show you why. You guys may remember, hopefully you haven't forgotten, or hopefully this quick review that I'm going to do will remind you about long division. And you have to use long division to be able to work through these. Now, if we have I to the power of, let's say, 33, you have to use long division. So I'm going to use my exponent there, 33, and I'm going to just divide it by 4 using long division. So I think, okay, what 4 goes into 33? That's 8 times. 8 times 4 is going to give me 32. 33 minus 32, that leaves me a remainder of 1. This value, 1, is the value that I'm looking for when I do this. Okay? Because I'm going to apply that remainder to my I. And remember, once we divide it by 4, your remainder should always be less than 4. Always, 100% of the time. If you have a remainder of 0, anything to the power of 0 is 1. So I to the 1, of course, is itself. Remember, you need to have that in your notes. I to the first, second, third, and fourth. All right. Anybody think they could try one of those? Doing the long division? I'll give you one to try here. Let's do I to the 37. Okay, give me an idea there, guys. Tell me what that's going to come up to. I'll give you about 1 minute to work that. Those of you that are watching on the recording can pause if you'd like. I like that. Angelina, I like that. Simplify that a little bit more for me. Here you go. Exactly. Perfect. That's it. Excellent. All right. So, a lot of correct answers there. Good job. So we take the exponent and we divide it by 4. It goes in 9 times. I guess I should have thought of an example with a different answer than the one that I just did for you, right? So, all right. So, got to move on. We got quite a bit to cover here. So, all of that was just leading us up to complex numbers. Complex numbers look like this. A plus BI. Okay. So the imaginary part is always the second part here. And this, of course, is in your lesson. I want you to thoroughly read through the lesson there. So we had a question in Unit 1 where you had to create your function. And it's probably best to use something linear in that particular assignment. And you basically could just replace your A and B with any numerical value. For example, I might say instead of A there, I'm going to use 4 plus 7i. This is a complex number. All right. Now, you've heard in a lot of you probably in English class actually have something called conjugates. We have conjugates in mathematics as well. When we talked about using just regular radicals, for example, if we had 2 plus square root of 7, the conjugate all we'd have to do is change that middle value there, the plus to a minus. Okay. So a conjugate, remember, all you do is change the sign in the middle. Let me show you a few mistakes that I sometimes see when we're dealing with conjugates. Sometimes we have, let's say we had negative 2 plus square root of 7. If I can write a 7 correctly, there we go. Now, remember, the rule is you just change that middle sign. So you're still going to have a negative 2 in the front there. And the conjugate to that would be negative 2 minus the square root of 7. Okay? So, something very important. Now, we do conjugates for imaginaries the same way. The reason we come up with a conjugate is it creates what's called a difference of squares pattern, basically. And it's going to help us eliminate certain values, such as radicals or imaginary numbers. So let's look at an imaginary number and a conjugate to that imaginary number. Let's say we have 4 plus 7i. If I want the conjugate, remember, all I have to do is change that value in the middle, just like that. All right. And let me write another one. I'm going to write another one down here really low on the screen because I'm going to actually use these examples to lead us into operations on complex numbers. So I write negative 3 minus I square root of 7. The conjugate to that would be negative 3 plus I square root of 7. Well, those of you that are in my class, when we do our DBA, I'm certainly going to give you some complex value or perhaps a value with a radical in it, and I'm going to ask you to tell me what the conjugate is. So you will simply change the sign in the middle. Okay. So let's go back up top here to this first example. And let's lead into the second lesson that you have this week, which is operations on complex numbers. All right. By the way, time-wise, we are trying to cover a lot, like I said. So I'm trying to spend a little more time on the complex and imaginary numbers. And through the polynomials, I'll move a little bit faster. So you guys probably remember FOIL, they call it. I think now the course wants you to think of FOIL as the distributive property, which it is the distributive property, but if you remember it better as FOIL, I want you to remember it the way that you're going to remember it best and have the most success, of course. So, first times first would be 4 times 4. If I want to do outside times outside, I'm just putting my negative sign here because it's going to be a negative times a positive, which is going to be minus something. So this just saves me the step of working through that. So I do outside times outside, and inside times inside, and then last times last. That's going to be a negative value as well. So the purpose of these conjugates, that's probably correct, Jordan. I haven't worked it out yet. I'm kind of working it out here live on the spot, so hopefully I don't mess it up. If I mess it up, be sure you correct me. So first here, 4 times 4 is 16. Okay, 4 times 7i. You treat the I just like you would an x, just like it were a variable. So that will be minus 28i, and then 7i times 4 over here. And we're noticing here in the middle something that's going to happen. 7 times 7 is 49, and then I times I is I squared. Well, once again, we have to remember that pattern of exponents. And look what happens here in the middle. Negative 28i plus 28i. It's just going to be gone, so it's 0. Now, 16 minus 49i squared. Here's where I see some mistakes. Is with the signs typically on these. Remember, I squared is negative 1. So 16 minus, and I'm being very careful here, showing every little step. Even though clearly we could do these in our head. But this is where I see a lot of the mistakes, is when we're trying to move quickly. And then we're trying to calculate in our head here. I'm being very careful here because this is getting tricky with my signs. Minus 49 times negative 1 is negative 49. And you can see this is going to be plus. And what would that be? 65, I think. Check my calculations if you have a calculator there. So, all right. So the next one there, we have negative 3 minus I squared of 7. This one's going to have a couple. I think I kind of start working on that one now with me, and let's see what we could come up with here. All right, so I'm writing out every step. So a lot of you can finish this faster than I can, but I just want to make sure everybody sees the entire process here. Then the middle, in our middle terms there, or what we call inside times inside, if you're thinking of it as FOIL, there's a negative times a negative, so it's actually going to be plus. And the last one is going to be, running out of room, sorry guys. By the way, that horrible handwriting over there on the far right says minus I squared of 7 times I squared of 7. So if that's a little hard for some of you to read, it looks pretty bad. All right, so let's go ahead and start simplifying over here. Yeah, negative 3 times negative 3 gives me a positive 9. And then I've got minus 3i root 7 plus 3i root 7. See, the same thing happens there with those middle values. All right, so over here at the end, we're going to have I squared. Then we have square root of 7 squared. Same thing as square root of 7 times square root of 7. So that's just actually going to be a 7 down there. Probably should mention that's another mistake that I see frequently. Because a lot of times students will change that to 49. Well, it's the square root of 49, which is 7. All right, and then we're going to once again be very careful with our signs. Remember, all these terms in the middle are canceling out for us. Minus I squared is negative 1. And square root of 7 times square root of 7 is 1. Okay? That's 9 minus negative 1 times 7 is negative 7. Which is just 9 plus 7, 16, just like that. All right, so the point of this, guys, is when this works the same, you know, if we did this problem and there was no I, there was just negative 3 minus square root of 7, the same result would occur. In other words, we got rid of the radical. In this case, we got rid of a radical and we got rid of an imaginary number. All right, so let's do some, and I'll move a little quicker through this because this next part is not quite as complex, I don't think. I think it'll make a little more sense to you because we're just going to treat our I value just like we would any variable, really. Okay, it's just that once we get exponents on that I value, we can start to maybe reduce it a little bit. Okay, simplify it, I should say. So let's say we have 3 minus 2i times 4 plus 3i. Okay, so we're going to do the same thing here. Like I said, a lot of you probably do some of these steps in your head. Well, instead of writing 3 and 4 in parentheses, I know that's time consuming. We obviously know that 3 times 4 is 12, but by taking extra time to write down each step and keep my work very organized, if I do end up making mistakes, it's going to make it very easy for me to go back and find those errors. All right, so plus 3 times 3i. Remember, we're going to multiply this just like we would if that I were an x or any other variable. And in the middle here, I've got a negative times a positive, so I know I'm going to end up with a negative value. So that's 2i times 4. Then at the end is a negative times a positive, so I'm going to just go ahead and write that as a negative now. And that's going to be 2i times 3i. Okay, so let's start breaking this down. 3 times 4, 12. 3 times 3i is 9i. And then minus 2i times 4 is 8i. In this end, we're going to have 2 times 3 is 6. And then I times I is I squared. I don't really have to write that in parentheses, but it's going to help me on this next step here. So 9i minus 8i, like I said, same thing if it were 9x minus 8x. That's just going to leave us with 1i. So I could write 1i, but we typically don't write those 1 coefficients. So I'll probably just write I when I write my final answer here. So minus 6i squared, but remember, I squared is negative 1. So 6 times negative 1, negative 6. Then we've got some like terms we can combine here. That's going to be 18 plus I. Remember when we said that complex numbers in the form a plus bi, okay? So I'm always going to write that imaginary value there on the right. And we're going to talk when we get to the next portion here on polynomials. We're going to look at writing those in ascending order and the number of terms and degree of terms and things of that nature. Another thing that we'll have is division with these. So let me show you. And this is going to make a lot of sense as far as why do we need to know those conjugates and all of these type of things. Well, we've got to get rid of imaginary numbers or radicals in the denominator. So let's say I had 3 divided by 7 times the square root of negative 1. Well, let's go ahead and simplify that as much as we can to get started. We know that square root of negative 1 is I. Okay, but we cannot have a radical or imaginary number in the denominator of a fraction. We have to do what's called rationalize it. Okay, like I said, we're covering a lot of material in today's lesson. So don't get frustrated if it seems like an awful lot of information coming at you at once. I know that it is. Remember, that's why we're in the class, is because we need to learn this material. So don't expect to have complete mastery of these concepts just by seeing me work through a few examples. I want to give you a better context as you're heading into the lessons. So you still need to make sure you're doing a lot of work on those lessons. Now, to get rid of this I in the bottom, remember we know that I squared is negative 1. So to get rid of something like that, I would just multiply this entire fraction by I over I. On the top, that would give me 3i, and the bottom would give me 7i squared. And then what happens is that gets rid of that imaginary value on the denominator there. So I squared is negative 1. 7 times negative 1 is negative 7. Now this is a positive divided by a negative. So in simplest form, I will write that as a negative value and negative quotient. So negative 3i over 7. That's how we would write that. Okay. Now, very important. I think this is in Unit 2, Lesson 7. You know, you have in your lessons these little areas that say Learn More, and you click on the link and it opens up a pop-up. That's going to have some extra examples on multiplying a complex number by its conjugate. So I certainly want to make sure that you're looking through those, because it has some important information that's going to help you when you get to a point where you're having to work through these type of problems. So, all right, let's look at one where we have to use a conjugate. Now, I'll try to use something similar to what we had up there. All right, so let me change the color of the marker here. I don't want anyone to think it's the same problem. We're working on a new problem now. And we'll do 7 plus I on the bottom. Well, we can't just multiply this by I over I and get rid of the imaginary number. And let me show you why. Let's say we multiply this by I over I. Well, 3 times I, that's 3i. It's okay to have the I on the top. We just can't have it on the bottom. Well, let's distribute here on the bottom. 7 plus I, quantity, times I would give me 7i plus I squared, which is going to end up being 3i over 7i plus negative 1, which is 3i over, remember we write the numerical part first here, so negative 1 plus 7i. So that still leaves us with an I, an imaginary value in the denominator. So that's the reason that we have to go over and understand those conjugates. When we multiply it by a conjugate, as you recall, we multiply it by a conjugate, we actually get rid of that imaginary value or radical. So let's multiply it by the conjugate here, 7 plus I over 7 plus I. Right? We talked about equivalent forms. I can multiply any fraction by 1 and it'll still equal itself. So when I multiply this by 7 plus I quantity over 7 plus I quantity, or anything divided by itself is 1, so I'm just multiplying this by 1. That's important to note, that we don't change the value of anything when we do this. All right, so yes, that is correct, Jordan, for the top. So we distribute the 3 on the top. 3 times 7, 21. And then 3 times I, so plus 3i. But on the bottom part here, remember we can see 7 times 7, 49. We do outside times outside. And inside times inside. And last times last. All right, so notice here in the middle, just like we've had with any conjugate, positive 7i minus 7i, that's 0. That's going to be gone for us. We still have an I there, though. We've got an I squared. Let's see what happens here. So 21 plus 3i. Remember, I squared is negative 1. That's 21 plus 3i over 49 minus a negative is just plus. This would be the simplest form, 21 plus 3i over 50. Okay? So that's going to cover what I'm going over as far as the complex and imaginaries. Remember, you know, just same way this ties in with the radicals that we were working on last week. This is going to be critical. You have to know this to be able to do the quadratics and the polynomial functions that are coming up later in the course. So very important that you're able to manipulate these, because all of this work is going to be a very small portion of a much larger problem when we get to our quadratics and whatnot. Okay? So, right. So moving on, we're going to look at the review of polynomials. And you've all had polynomials in the past. Algebra 1, I think even pre-algebra probably you've had them, but for some of you, Algebra 1 was a couple of years ago. All right, so it's certainly understandable that we need to have a bit of review here. All right. Now, someone asked, this is Microsoft OneNote that I use. Okay. Now, for review of polynomials, this is Unit 2, Lesson 8. So there's a little activity that you're going to want to do on the first page, and it talks about mono. When we say mono, these are just prefixes. We have monomial, binomial, trinomial, and then polynomial. So mono is one term, bi is two, tri is three. One of the things we learn, tri, that always means three, like a tricycle has three wheels. Poly doesn't mean four. A lot of times it will be four, but it just means many. So typically we're talking about more than three, right? So, because if it just had three terms, we would classify that as a trinomial. All right, so let's look at some examples here. We need to understand terms. We need to understand quite a few things. So first, I'll write 3x squared plus x minus 9, for example. And I'm going to kind of highlight these in different colors. 3x squared, I've got plus x, I've got minus 9. You may see words used such as how many terms are in this. You can have questions like this on your assignment. Let's see how many terms. Well, each one of these is a term. This is a term, this is a term, and this is a term. So in this case, there are three terms. You're also going to need to understand the degree. The degree is just the sum of the exponents on any term. So if I look at 3x squared, for example, my exponent there is 2. So it's a degree of 2. The degree of the x here is 1, and the degree of a numerical value, there's no variable with an exponent. Remember, anything to the power of 0 is 1. So if there were an x to the 0 there, it would just be a 1, so it would be 9 times 1, and the degree of any numerical term is 0. Now, that's the degree of each term, but it is not the degree of the trinomial. The degree of the trinomial is 2. So the degree when we're talking about a trinomial is specific to the term with the highest degree. So I'll give you a couple more examples of that. Let's do one with, let's look at a monomial, x to the 4th times y cubed. If I think of my exponents there, it's 4 plus 3. So the degree of this monomial is 7. Now, if that monomial is part of a polynomial or trinomial, let me give you an example. If we have x to the 4th times y cubed plus 7x squared y squared minus 4xy, I can look at the degree of each of these here. The first one is a degree of 7. The middle one is a degree of 4 because 2 plus 2. Sometimes I see a mistake on these. Remember, there's a 1 exponent on all of these that is implied. We don't write 1 exponent, just like we don't write y coefficients. So there is a 1 plus 1, in other words, a degree of 2. So these, again, are the degrees of each term. But when I talk about the degree of the polynomial or trinomial, it's only the degree, the highest degree that matters. So in this case, degree of 7. So if they asked me for the degree of the polynomial, I'd say 7. If they said, what is the degree of the middle term, I would say 4. So remember, for the degree of the polynomial, we don't add all of these degrees together. We just use the highest degree. All right. So let me give you guys one here. Let me change colors again. I want this to run together. I'm going to give you one. I want you to tell me the degree of the polynomial. And you can just type your answer right there into the chat box. So I've got x minus 9 plus 3x squared. And type in the chat box there. I'll give you about 30 seconds here. What is the degree of that trinomial? Seeing pretty much all correct answers. Good job. Right. There was one, someone wrote 3x squared. Let me look here. Someone wrote the degree is 3x squared. That's not the degree. Okay. But that is the actual term in the trinomial that's going to give us our degree. Remember, we're only looking at the sum of the exponents. This just has one exponent of 2. So the degree of this is 2. Now, I wrote this one a bit different than what you're used to seeing these in. You're going to have to identify the degrees on all of these because you're going to be asked to write them in ascending order. You're going to also be asked to write them in descending order. So we need to make sure that we know the degrees. And ascending and descending is pretty much exactly like it sounds. Sometimes we need to write ascending, obviously just going up, 1, 2, 3, 4, 5, 6, or 0, 1, 2, 3, 4, 5. And then descending, we would just go backwards. All right. So let's look at this. And see, let's get all our degrees here. X has a degree of 1, the minus 9 has a degree of 0, and the 3x squared has a degree of 2. So if they ask me to write it in descending order, that means I want it in 2, 1, 0, descending, right? I want to write it as 3x squared plus x minus 9. You also notice it's very critical that you take the sign with the value. That's another mistake that I sometimes see, is not taking the sign with the value. So we're going to make sure we keep all of those signs with our values there as we're moving them around. So let's look back up at this one. Up here, the x to the 4th y cubed plus 7x squared y squared minus 4xy. This one's already in descending order. There's no term with a degree of 6 or a degree of 5 or a degree of 3. So descending order, 7, 4, 2. Now this is typically the way you're always going to write your trinomials and polynomials. All right, always. Now, the only time we're not going to write them in descending order is when they actually tell us, look, we want you to write it in whatever other order. They say ascending order, ascending, starting from 0 and then counting up. Then we would have to change this around. Remember to bring that negative sign with your 9 value that has a degree, or 0 rather, plus x plus 3x squared. They do have some questions that are going to ask you to write this in ascending order, but they're few and far between. For the most part, you're going to write everything in descending order, unless they really specify. And when they ask you a question like that, they're just trying to determine if you're able to find the actual degree of those, and then, ascending and descending, ascending going up, descending going down. Okay? So, let's look here. Oh, by the way, remember this was in descending order, and the entire trinomial had a degree of 7. That's the x to the 4th y cubed. I'm going to point that out again. Probably going to see some questions similar on that. So the last thing that we need to cover, and we've only got 12 minutes left, so we actually did pretty good on time. But this is polynomial operations, and this is probably I probably wish I had a little more than 12 minutes to cover it. But we're going to go through adding them, subtracting them. I don't think this lesson covers dividing them. But if it does, I just posted a ton of resources on these polynomials because we're probably not going to have time to get to every single operation on them. So let's just add some together first. So starting out here, we're going to do, let's just do 3x squared plus 2x minus 3 plus 4x squared minus 3x plus 8. All right, now, I only put those in parentheses because that's the way your questions are going to be posed on a test or quiz. Some of the auto-graded assessments that you do, they're going to put them in parentheses. It's pretty critical when we're subtracting. Yes, Bria, that 8 looks pretty bad, doesn't it? Let me change it. One of the things that you're going to notice is they're going to put parentheses around, because when we subtract these, it's going to be critical that we have the parentheses, because you have to distribute any coefficient that may be outside of those parentheses. In other words, they're wanting you to think of this as plus 1 times 4x squared minus 3x plus 8, okay? But when we're adding, I mean, 1 times anything is itself. So in this particular case, when we're adding these trinomials, well, it's pretty easy to just say, I don't really need the parentheses there. I'm not going to change any value. Okay. Now, most of you are pretty good with your like terms, finding your like terms and combining them and whatnot, but like I said, a lot of you, it's been a long time since you've done the Algebra 1, so I want to make sure that we cover this. Like terms have the same exact variables. Now, all of these have a variable, the variable's x, but there's a big difference between x squared, which is x times x, and just x. So when we're combining like terms, we can only combine these that have the exact variable. This is 1x, just one plain old x. It's a lot different than the x squared. So you can't combine these x squareds with the x's. In other words, they're still going to have terms with just an x and terms with an x squared when we simplify this. Now, obviously the numerical values, those are pretty easy. We can always combine plain old numerical values. But you might remember back from some of you, it's probably middle school or earlier, where you talked about different properties of numbers, such as associative property and commutative property. Those properties allow me to move these values all around. So I'm going to write these like terms together, 3x squared plus 4x squared. I like to cross them out after I write them down. I don't write anything more than once, and I don't forget any terms. I know, okay, well, I've written all my x squared terms down. And we're going to do plus 2x minus 3x. And then I'm going to do minus 3 and plus 8. So I use the associative property to just move these around as I see fit. I suppose in some way you could say, well, not really. We didn't really use commutative property here. Right, that would be if we were to switch, like the 3 and 8, for example, would be a good example of commutative property. So now that I've got these together, 3x squared plus 4x squared is 7x squared. 2x minus 3x is minus 1x. But remember, we don't really write those 1 and negative 1 coefficients. So it would just be minus x. And negative 3 plus 8 is 5. Yeah, Jordan, that's fine. I'll have this posted up here later today. All right. So the degree of this trinomial I ended up with is what? What is the degree there? Type that in the chat box for me. Exactly. I like seeing that. I'm seeing about 50 correct answers. So I don't see any incorrect answers. So that's very awesome. Thank you. All right. So it's a degree of 2 because our terms here. That's a degree of 2, that's a degree of 1, that's a degree of 0, and for the degree of the trinomial, we only use the highest degree, which in this case is 2. So, is this written in descending or ascending order, or neither? You can type right in the chat box there. Is that descending, ascending, or neither? Correct, correct. Excellent. All right, so it's descending because we're going down. I could write it, obviously, if I wrote 5 minus x plus 7x squared. That would be ascending, but this is typically the form that you're always going to want these in. Descending order there, okay? So let's do some, that was just regular addition. The tricky part, we're going to use, let's use the same exact question here, except instead of adding, we're going to subtract. Let's see if that makes a difference. So we've got 3x squared plus 2x minus 3 minus 4x squared minus 3x plus 8. Where I see a ton of mistakes, and even when you actually know what to do, a lot of times I'll see students make some errors. Right? Because this negative is subtracting this entire quantity over here. So this is the same thing as minus or plus a negative 1 times that quantity. In other words, you have to distribute that negative all the way through. All the way through. Basically just going to flip the sign of every term there. So I'm going to go ahead and I can write this portion on the left without the parentheses at this time. But this is going to be minus 4x squared minus a negative 3x. A minus a negative 3x is actually plus 3x, then minus 8. You see all these signs here. That one was positive, now it's negative. That one was negative, now it's positive. That one was positive, now it's negative. So what that did was that actually flipped every sign that was inside those parentheses there. So something to keep in mind. All right. Now let's go ahead and just look at where our like terms are. 3x squared minus 4x squared, and then 2x and 3x, and then minus 3 and minus 8. I just wrote them all together. Like I said, it seems maybe like an extra step that's not really something all of you would need, but this helps cut down on the errors. This is going to give me negative x squared plus 5x minus 11. But the purpose there, guys, like I said, make sure that you're distributing that negative value, okay? All right, so let's look at some multiplications. We're going to do several multiplications, 3 actually total, but I only have about 3 minutes left. So those of you that do need to get to your next live lesson, I certainly understand if you need to take off and get to your next lesson. I am going to leave the recording going here until I finish all 3 of these additional multiplication examples that I wanted to get through. And those of you that are able to stay, of course, certainly feel free to do so. All right, and I'll work through these reasonably fast. So, but I know there are some of you that have history lesson that you have to get to. All right, so multiplying 3x squared times 4x squared minus 3x plus 8. I'm kind of using these values because those are the ones I used in all the examples. We're trying to keep them the same, but obviously the operations that we're doing on these are very different. Okay. So in this, once again, we're just going to distribute. You're going to see a lot of use of distributive property here all throughout the course. Right. So to distribute there, 3x squared times 4x squared, and just I would want you to write it down 3x squared times 4x squared like that. But just for time reasons, I'm going to go ahead and kind of break the rule here myself, I guess, and go ahead and kind of calculate these a little quicker in my head. So 3 times 4 is 12. Then x squared times x squared is x to the 4th. Remember, when we're multiplying like bases, we just add the exponents. Okay. Then 3x squared times a negative 3x. I know that's a positive times a negative, so it's going to give me a negative value. That's minus 9x cubed. And 3x squared times 8 is 24x squared. And that's all we would do with that. Okay. Interestingly enough, next unit goes over factoring, so we'll be taking something like this answer and taking the 3x squared out of it. So we need to make sure we could go back and forth on these guys. All right, so let's do a couple more, 2 more here. And I'll kind of change the color for each one so we don't think that any of these are the same problem. So 3x squared minus 3 times 4x squared plus 8. And this is back to the distributive property, or as I said, some of you refer to it as FOIL if you're successful. And if you're successful using the FOIL and getting through these and getting correct answers, I do not want you to stop using that. But they are just referring to it as distributive property now, apparently. But, first times first, 12x to the 4th. Outside times outside is the 8 times 3x squared. So that's 24x squared. And then inside times inside minus 12x squared. Last times last minus 24. You notice in this case we end up with some like terms in the middle. So we do have to simplify that a bit further. 24x squared minus 12x squared is plus 12x squared minus 24. And that would be as far as we could go on that one. It's interesting that our ending trinomial there has a very obvious GCF of 12. And those of you that want to review on the GCF, please check those links I put on the message board. We've got some great ones on there, and some really good ones on there about the GCF, and we're going to get a lot deeper into factoring here, I think, next week or the week after. So, all right, last one. These are sometimes a bit more difficult for students. So I'm going to show you a couple ways to do these. Actually, I guess I'll just show you one since we're so far past our time limit here. All right, so when I have something like this, it's not a simple FOIL because on the right I have a trinomial, on the left I have a binomial. What I like to do on these is just focus on one term of the binomial at a time. In other words, I'm going to think of distributing the 3x to every one of those terms. Then I'm going to distribute the negative 3 to every one of those terms. All right, so 3x times 4x, that's 12x cubed. 3x times negative 3x is minus 9x squared. And then 3x times 8 there on the end. All right, so now let's think of our negative 3 being distributed to everything. Negative 3 times 4x squared, negative 12x squared. Negative 3 times negative 3x is plus 9x, and negative 3 times the 8 gives me a negative 24. But you'll notice here we end up with a few terms that we can combine here and here. And also I have an x term here and an x term here. So I can combine all of those. And let's see what we end up with. 12x cubed. Remember, I'm still writing this in descending order. So this is minus 21x squared plus, these are going to give me 33x, and minus 24. All right. So what to think of on these? A few things we could think of here. Now, first of all, it's a good question. Thanks, Angelina, for watching out for me there. 33. 24x plus 9x is 33x. Thank you very much. Yeah, but it's a good thing you told me that before I, left it on the recording as an error. That would have been confusing. Now, a few things to think about. Is this a monomial, binomial, trinomial, or polynomial? And type your answer in the box there. Correct. Okay, good. And what is the degree of the polynomial? Correct. Good. Is it prior? That's close. I know my handwriting's bad. Negative 9, negative 12 are the x squared terms. That's the negative 21 there. Good. All right, and then it's in also, obviously, it's in descending order, which is, like I said, that's typically what everything's going to be. I'm going to stop the recording and stop the share.